series, there is something known as backshift notation, which is a very useful device to represent the lagged values of a time series. So the backward shift operator is represented by B, and B acts on yt, which is your time series of interest. So if y is the measured value of the observed value of y at time t, if you put b in front of it and b is an operation on yt, then you would get yt minus 1. So what you're doing essentially is lagging your time series one period back, okay? And that's why it's called the backshift operator. And this is sometimes in some books, this is also referred to as the lag operator, which is represented by L. So L times yt will give you yt minus 1. So you can use whatever you like, B or L, they both do the same thing. Okay, one is called backshift operator, the other one is called lag operator, but they work the same way. The idea behind the backshift or the lag operator is that it is going to shift the data back one period. But in practice, we can also try to iteratively move the data back more number of periods. So if we had, for example, an operator B on B of yt, then this would become B square yt, and this is essentially trying to lag the time series 2 periods back, okay? And so this can also be written as L square yt, which is just saying this is yt minus 2. In practice, you can have, in general, I guess you can try to write down some kind of an expression like this, where you could say b to the m, right? This is the power on yt equals yt minus m. So you're lagging the time series m periods back, and the same thing for if you use L. Now for monthly data, if you want to use the backshift notation and you want to talk about the same month last year, then b to the 12 is used. Okay, so you can say b to the 12 of yt. So this is talking about the value of, for example, January of 2019. So the backshift operator or the lag operator is a very convenient tool that is used for describing the process of differencing. If you want to use the backshift notation for first differencing, then you can rewrite the expression of the change in yt, which is yt minus 1, in the following way. You can rewrite yt minus 1 as b times yt, and then rewrite this expression as 1 minus b times yt. So what you have essentially here is that the first difference is now represented by 1 minus b in this case, okay? Because the first difference is yt minus 1. So the first difference is 1 minus b. If you wanted to do a second order differencing, then that would be 1 minus b whole square operated on yt. Now remember that the second order differencing is not the same as the second difference. The second difference would be represented by 1 minus b squared, but what we are usually interested in is first order differencing or second order differencing to make the time series stationary. In general, a dth order difference can be written as 1 minus b to the d times yt. Okay. If we were trying to do a seasonal difference followed by a first difference on yt, you want to make sure that the first type of differencing that you do is written next to yt. So this is the seasonal differencing, and then the first differencing is step number 2. So this comes after the seasonal differencing is done. So you can play around with this algebra and you can try to rewrite the expressions and expand on those if you were actually doing seasonal differencing first, followed by first differencing, then you can actually multiply these together, these backshift operators. Okay, so here we're just really multiplying um, these two expressions here, and what we get in the end is yt minus 1 minus yt minus m plus yt minus m minus 1. So you have, this is really just saying here you have the first term, which is your first order differencing, but you also have your seasonal differencing, which is what we did in the first place.